Let's learn about a last in, first out data structure called stacks. Every time you press Ctrl+Z to undo, you're using a stack. The last action you took is the first one that gets undone. This simple principle, last in, first out, or LIFO powers, undo buttons, function calls, and countless applications. Here, each action you perform is pushed onto the stack. When you press Ctrl+Z, the apply bold action is popped off the stack, and its effect is reversed. This demonstrates how the most recent action is always the first to be undone, perfectly aligning with LIFO. The type word action is then popped, and the text is removed. The stack continuously keeps track of your actions in reverse order of their execution. Finally, type hello is popped, clearing the document. This entire undo mechanism is a practical application of the last in, first out principle. This principle isn't just for software. Imagine a stack of plates in a cafeteria. It's a real-world analogy that helps clarify how stacks operate. You add plates on top, one by one. Each new plate goes on top of the previous one, just like pushing items onto our digital stack. When someone takes a plate, they always take the one at the very top. This means the last plate you put down is the first one taken, which is the core idea of POP and LIFO. No reaching into the middle, no taking from the bottom. Only the top matters. This restricted access is a defining characteristic of a stack. It's not a limitation, but rather the very mechanism that makes stacks so effective for specific tasks. Here, we visualize the same stack data structure through two different lenses. An application interface on the left and its abstract representation on the right. The connection line emphasizes that these are two views of the same underlying action. Adding B pushes another item onto the stack. Deleting B then pops it off, reversing the last action. This clearly shows how the application's undo system directly manipulates the stack data structure. This dual perspective helps us understand that while applications present a user-friendly interface, behind the scenes, fundamental data structures like stacks are at work, managing information efficiently. The two primary operations for a stack are push, to add an element to the top, and pop, to remove an element from the top. Here, we push 4 blocks onto the stack, demonstrating the additive process. Now, we pop the elements off. Notice how block 4, the last one pushed, is the first one to be popped. This consistent behavior is what makes stacks predictable and powerful for specific programming patterns. This fundamental behavior is precisely articulated by the equation. Last item pushed equals first item popped. This mathematical statement encapsulates the entire principle of LIFO, or last in, first out. While stacks are governed by the LIFO principle, another essential data structure, the queue, operates on a different but equally important rule. First in, first out, or FIFO. When adding elements, both structures take new items. For the stack, we push them onto the top. For the queue, we enqueue them into the back or rightmost available position. The key difference emerges during removal. The stack pops elements from the top, always the last one added. The queue, however, dequeues elements from the front, always the first one that was added. This is how the queue preserves order. This side-by-side comparison clearly illustrates that a stack inherently reverses the order of items, while a queue strictly preserves it. Understanding this fundamental difference is crucial for choosing the right data structure for your needs. A defining characteristic of a stack is its single access point. You can only interact with the topmost element. Attempting to access an item deeper within the stack, like block B here, is simply not permitted. To access any element deeper in the stack, you must first remove all the elements above it. Only when an item reaches the top does it become accessible for operations. This strict protocol ensures the integrity of the LIFO principle. This single access point isn't a flaw. It's the fundamental design choice that makes stacks incredibly efficient for managing ordered sequences where only the most recent item is relevant. By the end, you'll recognize stacks hiding everywhere in software and understand exactly when to use them. Now let's formalize the stack concept. A stack is a data structure with two fundamental operations, push and pop. Push adds an item to the top of the stack. Pop removes and returns the item from the top. That's it. No searching, no sorting, no random access. Every operation happens at the top, and every operation is O of 1. Constant time. This means push operations always take the same amount of time, regardless of how many items are already in the stack. This simplicity is the stack's greatest strength. You can't grab the third item without popping two items first. This constraint is intentional. It forces clean design and guarantees predictable behavior by ensuring only the most recently added item is accessible. Just like push, pop is also O of 1, constant time, always taking the same amount of time. Let's see how push and pop work in practice in a dynamic scenario. Notice how the top pointer continuously adjusts, always marking the current topmost position, which is critical for maintaining the stack's last in, first out order. Beyond push and pop, some stack implementations offer a peek operation. Peek allows you to view the item at the top of the stack without removing it. This operation is also O of 1, constant time, and is fundamentally non-destructive, meaning it doesn't alter the stack's state or its contents. The top pointer isn't just a visual aid. It's the core mechanism. It tracks the current position of the last item added, acting as an index that points to the next available slot or the current top element, depending on the implementation. In an array-based stack, this pointer is literally an index variable. Ultimately, a stack can be understood as an array with a specific last-in, first-out constraint. The top pointer, or index, dictates where new items are added, and from where items are removed, strictly adhering to this LIFO principle. This combination of an array's contiguous memory and the LIFO rule defines the stack data structure. Stacks solve real programming problems every single day. When you call a function in code, the system pushes a new frame onto the call stack. Each frame represents an active function holding its local variables and the return address, indicating where execution should resume once that function completes. This sequential stacking demonstrates the call order, with the most recently called function always at the top. When a function completes its execution, its frame is popped off the stack. The return address, stored in the calling function's frame, tells the program exactly where to pick up execution. This last in, first out, or LIFO principle ensures that program execution always returns to the correct point in the calling sequence. This mechanism is fundamental for managing program flow, allowing complex nested function calls to execute and unwind predictably. Notice how each frame explicitly stores the return address, guiding the program back to the exact line of code after the current function completes. When an error occurs, the call stack provides a stack trace, a snapshot of all active functions leading up to the error. This trace reveals the exact sequence of function calls, from the initial main function to the one where the error originated, helping developers pinpoint issues. Beyond function calls, stacks are also crucial for syntax validation. When you write code with nested brackets, curly braces, parentheses, square brackets, the compiler uses a stack to check that every opening bracket has a matching closing bracket in the correct order. As the code is scanned, each opening bracket encountered is pushed onto the stack. When a closing bracket is encountered, it's compared with the top element of the stack. If they are a matching pair, the top element is popped. After processing the entire expression, if the stack is empty, it signifies that all brackets have been correctly matched and the syntax is valid. But what happens when there's a mismatch? If a closing bracket does not match the top of the stack, it immediately signals a syntax error, preventing incorrect code from executing. To summarize, stacks power function calls, enabling proper execution flow, and they are also critical for validating syntax, ensuring your code adheres to structural rules. Stacks are everywhere. Text editors use stacks for undo and redo. Web browsers use stacks for back and forward navigation. Compilers use stacks to parse expressions and enforce syntax rules. Graph algorithms like depth-first search use stacks to explore deep paths efficiently. Every function call in every program uses the call stack. But stacks are not a universal solution. They're specialized for LIFO problems, meaning last in, first out. If you need FIFO, first in, first out, you should use a queue instead. If your problem requires random access, an array or a list would be a more suitable choice. Stacks give you guaranteed LIFO ordering and O of 1 push and pop operations, making them fast and predictable. However, stacks are not without limitations. Fixed size. Stacks can lead to a stack overflow if you attempt to push more elements than their allocated capacity. Conversely, trying to retrieve an element from an empty stack results in a stack underflow. Error. These are critical conditions to manage. This highlights a key trade-off. Fixed size. Stacks are fast and predictable but carry the risk of overflow, while dynamic stacks are safer and more flexible, as they can reallocate memory to grow, though this comes with a slight performance cost. To illustrate a practical example, consider how web browsers handle navigation history. Each time you visit a new page, it's pushed onto a history stack. When you click the back button, the current page is popped off, and you return to the previous one. Ultimately, the key skill is choosing the right data structure for the problem at hand. Stacks sacrifice random access for simplicity and speed. Understanding this trade-off, and when to apply a stack versus a queue or an array, is what separates beginners from experts.